Hi everyone. In this video, we will examine conditions under which a given function f from R2 into R is integrable. In the previous video, we looked at a theorem related to when a double integral could be calculated as an iterated integral. And one of the important hypotheses of that theorem was that the function f needed to be integrable. However, if we have to prove that from the definition, then the iterated integration theorem is not particularly helpful because in the definition, we generally speaking need to know the value of the integral itself. So there would be no usefulness in calculating these as iterated integrals if we first had to prove integrability itself, which would therefore necessitate already knowing the value of the integral. So what we'd like in this video is to be able to establish some conditions under which the double integral of f will exist just by knowing properties of the function f itself. So if we think back to the case of a function from R to R, like we examined in 5610, we actually looked at a couple of different theorems that told us under what kinds of conditions a function f would be integrable. In particular, we looked at theorems that said if f is monotone, then it would be integrable, and if f was continuous, then it would be integrable. Now, the monotone part is a little harder to replicate for a function from R2 to R, simply because we'd have to be a little more careful about what we mean by monotone, right? Because what does it mean for the inputs, which are now vectors, to increase? Well, that necessitates some sort of ordering on the inputs. It would be hard to maybe prove something like that, although you could probably work something up. However, continuity is something we've seen, and it's very reasonable to expect that continuous functions are, generally speaking, relatively well behaved. Maybe we can prove that every continuous function f from R2 into R is also integrable. So that'll be sort of our first goal for today, will be to establish such a theorem. So here again is sort of the big theorem we want to prove for today. So if a function f is continuous on a rectangle Q, again, this rectangle Q is just AB cross CD as before, then that function f is integrable on Q. So that's sort of the first part of this theorem. If my function is continuous on this rectangle in R2, then my function must be integrable on that rectangle. The second part of this theorem says, moreover, the value of the integral can be obtained by iterated integration so that the actual value of the double integral of f over Q can be written as first integrating with respect to x and then integrating with respect to y, or integrating first with respect to y and then with respect to x. Now, if you think back to that iterated integration theorem, there are more hypotheses there than just that f is integrable. So in order to apply that iterated integration theorem, you need f to be integrable, but you also need to define a function a of y, and that needs to exist for every y in CD. And then that function itself also needs to be integrable. So in this moreover part, there really is, this isn't just a simple consequence of the first part, there is more to prove here. So as we think about proving this, we're actually going to break this up into two stages. The first thing we want to prove is that if f is continuous, then it is integrable. Once we do that, we'll then show that given that f is continuous and now we know it's integrable, it also satisfies the other hypotheses necessary to know that we can calculate this via iterated integration. All right, so that's the plan. Before we jump into that, I would encourage you to go back to your notes from Math 5610 and just take a look at the proof there for the fact that a continuous function is integrable. Okay, so as just sort of a brief reminder there, okay, in that case, we essentially did the following. We said, okay, I've got some continuous function on an interval AB. Okay, because it is continuous, I can choose a really fine partition or a fine enough partition, right? And again, it doesn't have to be equally spaced, but we define the norm of a partition. And basically, I can choose this partition small enough so that on any little subinterval, the difference between the highest point and the lowest point, I can make it arbitrarily small. And like, I think in that case, you want to choose like epsilon over b minus a. okay? So I can choose this partition so that all of these are small enough. And then essentially what you do is you show then that this means that the upper integral of f, you show that this means that the upper integral of f minus the lower integral of f can be made arbitrarily small. You can do this for any epsilon, which then implies that the upper integral of f is equal to the lower integral of f. Okay. Now, we're going to do almost exactly the same thing here. It's just that, well, now we're working over a rectangular domain, our partitions, we just have to be there's just a little more notation involved. But if you go back and try to refresh yourself about the proof of the theorem that continuous functions from AB into R are integrable on AB, I think it will help you as we work through this proof see that the spirit of the proof is very much the same. It's just that some of the details have to change because our domain is now rectangular. All right. So let's get started. All right. So the first thing we want to show is that under these conditions, under the condition that f is continuous on Q, then f must be integrable on Q. Okay. So let's sort of think about, okay, what's my goal? If I want to show that f is integrable, then I want to show that the lower integral is equal to the upper integral. So we want to show that, say, the upper integral of f is equal to the lower integral of f. Okay. Now, how do I do that? Well, one way to do that would be to show that I can find some step function that lives above f and some step function that lives below f, such that the difference between the integrals of those step functions is as small as I would like. Okay. So to that end, we will show that for every epsilon greater than 0, there exists step functions s and t with s being less than or equal to f being less than or equal to t on Q, such that the difference between the double integral of t over Q, that's the upper step function, minus the double integral of s over Q can be made less than epsilon. So for every epsilon, I want to show I can find two step functions so that the difference between their integrals is less than epsilon. All right, now, how am I going to do this? Well, I'm going to pick an arbitrary epsilon, and I'm going to tell you what the s and t step functions ought to be. So I'm going to sort of prove this by construction, right? I'm going to construct the step functions s and t that do this. All right, so this is sort of, I would describe this as our game plan. Now we've got to actually execute this. All right, so let's take an epsilon. Let epsilon greater than 0 be given. All right, now the way I'm going to do this, one nice way to think about this. So let's draw sort of a sketch over here to help us as we go through this. So here I am in R3. I have some function. Maybe it looks sort of like this. I'll sort of draw some wavy surface, and I'm working over some rectangle Q sitting down here. Okay. Now, the first thing I want to do is I want to partition up this rectangle. Okay, but again, if I think back to the proof from 5610, and I don't want to do this, I don't just want to take an arbitrary partition. What I want to do is I want to pick my partition so that if I look at one of these particular rectangles, so say I look at, this is QIJ here. Okay, so say I look at the rectangle QIJ that's shaded in here. When I map it up to the surface, okay, now think about what happens when I map it up here, right? I'm going to get something, it's not going to be a rectangle necessarily anymore because it's mapped up and hitting this surface, right? But I sort of imagine this is the extension of this little rectangle here. Okay. I want to do this in such a way that the difference between the highest point on this mapped rectangle and the lowest point on this mapped rectangle is as small as I would like. Okay. Now, how do I know I can do this? Well, I know I can do this because my function is continuous. Because my function is continuous, if I choose a small enough rectangle, right, then my function values can't deviate too much on that rectangle. Okay. So formally, how we're going to do this is we're going to say choose a partition P of the rectangle Q. And right, this partition P, it'll be some x values, say x0 up to xn, cross y0 up to, we've been using ym, but we're going to use m for something else here. So I'll take this one up to yp. So choose this partition of Q such that if we define capital M ij to be the maximum value of the function f of x, over here, the maximum value of f of x for all x in Qij, and little m sub ij to be the minimum value of f of x for x values in Qij. Then we want Mij, capital Mij minus little mij to be less than, and this is going to seem a little strange at first. So I want it to be less than this quantity. Okay, so let's pause for a second. So capital Mij is just saying on this little sub-rectangle, when I map it up to the surface, what's the largest value I get out? Little Mij, okay, when I map all my values from this rectangle up to the surface, what's the smallest value I get out? This function is continuous. By the extreme value theorem, it actually has a maximum and a minimum. Okay. Okay, so that's fine. I want to choose this though so that the difference between these maximum and minimum values, this is epsilon over this quantity. And actually, sorry, there's actually a mistake here. This should be D minus C. Now, notice, if you, again, go back and look at that proof from 5610, we did something similar where we had an epsilon over B minus A, where B minus A was the length of our interval. Well, B minus A times D minus C, what is that? That's the area of the whole rectangle Q, right? So this quantity, I'm really taking epsilon over the area of Q here. So again, it's really doing something very similar to before. All right, so again, so far the idea is choose this nice partition so that over this partition on any sub-rectangle, my maximum and minimum values aren't too far apart. They're no further apart than epsilon over B minus A times D minus C. All right. And sorry, this should hold for 1 less than or equal to I, less than or equal to N, and 1 less than or equal to J, less than or equal to P. So essentially it holds on every one of the subintervals or subrectangles. All right. So now I need to define S and T. Okay. So I'm going to let S of X be equal to little m ij, and T of X be equal to capital M ij on the interior of each rectangle. Okay. So you have a problem with the boundary because the boundary is where the different sort of pieces meet, right? So you have a little problem on the boundary, but on the interior of each one, let me define these functions just to be the minimum value and the maximum value. So if you think about this function, the step function s of x so far, what we're really doing is we're saying come on each little subrectangle and choose the height to just be whatever the smallest function value is on that little subrectangle. So you're getting this little flat piece. You're almost approximating this blue surface by little rectangles from below, right? It's almost like a Riemann sum in a lot of ways, right? But you're choosing your sample point to be wherever the minimum value happens to be. All right. Now this defines everything on the interior of each rectangle, but we also need it on the boundaries. So let this and this on that. And for x on a boundary, set s of x to just be the minimum of f of x on the whole rectangle, and t of x to be the maximum over the whole rectangle of f of x. Okay. So the idea is, if you think the boundary line, so it really doesn't matter for the value of the integral, right? What happens at the boundary lines of these partitions. What really matters is that I need this s and t to satisfy this. So now the way I've set it up, s is going to be less than or equal to f. Why? Well, for each x value that's on the interior of one of my subrectangles, then s is equal to the minimum value on that subrectangle. So it's certainly less, s of x is less than or equal to f of x for each value that's on the interior. If I'm on a boundary, right, then s of x is equal to the minimum value of the whole function, right? So certainly it's less than or equal to f of x. Similarly, t is greater than or equal to f of x, right? And you go through exactly the same argument. On each subrectangle of the partition, t of x is equal to the maximum on that subrectangle, and t of x on any boundary line is the maximum of the function over the whole rectangle. All right, so we've set up these functions s and t. They're step functions. They satisfy this condition. Now we would like to show that their double integrals satisfy this condition. If so, then we're done with this first part of the proof. All right, so let's see if we can build out the rest of that. I'm going to keep this top part since that sort of outlines our game plan. All right. So now we want to look at this difference. Okay. So let's first look at each of these separately. So also, we have, if I look at the double integral of s over q, well, the s is a step function. So I can calculate the double integral of a step function as just a double sum. Right, this is the sum I equals 1 to n, sum j equals 1 to p of the values of this function on the squares, but that's just, sorry, this is for s, it's little m, ij, times the delta xi, delta yj, right? So it's really area of the rectangle times the height of each step, okay? And similarly, the double integral of t over q, again, it's just a step function. So it's just going to be this double sum. I equals 1 to n, j equals 1 to p, of capital M sub ij delta xi delta yj. All right, so great. I can now calculate the difference. And so the difference between these two. So I can write out what each of these is, but these are both finite sums, so I can collapse everything together. So this is actually just equal to a double sum I equals 1 to n, j equals 1 to p, of capital M sub ij minus little m sub ij times delta xi times delta yj. But I know something about this quantity, right? At the very beginning of this proof, I assumed that I chose my partition such that this difference was less than or equal to, and so this piece right here is going to be less than or equal to, this is again a double sum, I equals 1 to n, j equals 1 to p, of I chose this to be less than or equal to epsilon over b minus a times d minus c. And then the rest of this is just along for the ride, delta xi, delta yj. All right. But now if I look at this, this doesn't depend on I or j, right? So this is just a constant as far as these sums are concerned. I could actually pull these out of, and pull this out of the sum. And now I have this quantity, which if I just, it's like sort of stare at it, it's not immediately clear what it is, but you could actually work out algebraically why this is true via some telescoping sums. But what is this quantity? This is the area of the ijth subrectangle. And then I'm adding up the areas of all the subrectangles. I have to get that this quantity, this is just the area of Q, which is equal to the sum of the areas of all the Qij's. Okay. And so what we end up with here is that this is really just epsilon over b minus a times d minus c times the area of Q, which is just b minus a times d minus c. And so then just some quick cancellation, right, gives us here epsilon. Okay. And so after all of this, right, what we've shown is that by choosing a clever partition using the continuity of f, I can construct step functions s and t with s less than or equal to f less than or equal to t, such that the difference between the double integrals of t and s must be, and sorry, this should actually be, right, that's strictly less than, right? This inequality here was a strict inequality, right? So strictly less than epsilon, okay? And therefore, we have shown that the upper integral of f is equal to the lower integral of f by showing that I can construct these step functions that get arbitrarily close together. All right, great. So what's the end result here? Well, the end result is now I know my function f is integrable, right? So now just by knowing it's continuous, I know it's integrable. That's helpful, but again, as we mentioned at the onset of this, that's not the only hypothesis needed in order to say that your function can be evaluated via repeated integration. So we actually need to go a couple of steps further to get that sort of second half, the moreover part of the theorem. Now, turns out that there are two additional hypotheses. Again, you need that a of y function to exist, and you also need it to be integrable. The existence piece is actually fairly straightforward. The integrability takes a little bit of an argument. So we'll step through those pieces just to see how that works. All right. So again, the second part of this is proving this iterated integration piece. Okay. And so again, similar to before, let's sort of make a game plan first. So let's just prove. I want to prove that the double integral over Q of f. Let's first, let's just prove this one, this order. Okay. We'll prove this order and then we'll go, oh, to prove the other order, you just flip some things around. It's almost an identical proof. Okay. So we'll prove this part first, and we'll do this by doing two things. So first we'll show that this function, which in the iterated integration theorem was called a of y. So a of y, which is this inside theorem, or sorry, this inside integral. I need to show that this exists for all y in CD. Okay, that's the first thing I need to show. Okay, the second thing I need to show is that this function a of y is integrable on CD, right? Because essentially, right, what I need to do is I need to show that for this thing, I need to show this is going to exist. That's the first part. This is going to exist for every y. And then once it exists for every y, I then need to show it's actually integrable, right, on CD. All right. So this is sort of our game plan. Okay. So again, the first part is the easier of the two parts. Okay. So for the first part, what I want you to sort of think about is if I freeze a particular y value, so for a fixed y in CD, what is this function? Well, it's now for a fixed y value, so y is fixed, this is now a function of one variable, x. And since f of xy is assumed to be continuous, when we fix the y value, then this is still a continuous function of the single variable x. So for a fixed y value, f of xy is a continuous function of x on the interval AB, because it's continuous on the rectangle AB cross CD, right? And one way to sort of think about this is it's continuous on this rectangle, which is AB cross CD. And now what you're doing is you're fixing a y value. So now your function restricted here is continuous on the interval AB just for that fixed y value. Okay. Well, again, this is a continuous function of one variable on a particular integral or a particular interval. So it's integrable. Okay. So f of xy, again, y is fixed. So this is just a function of the single variable x, is integrable on AB. Okay. And well, what does that mean? And so a of y equal to the integral from a to b of f of xy dx exists, okay, for each y in CD. Okay, so really again here you're just using the continuity to give you the integrability. The key here is that this actually just reduces to a one variable problem, right? Because you're imagining y is fixed. So for each fixed y, this integral must exist because for each fixed y, this is a function of the single variable x, and it's a continuous function of the single variable x. So if you take a continuous function f of xy, you make a restriction on the variable x, you now have a function of one variable, which also must be continuous. Okay, the restriction of a continuous function is continuous. Okay. All right, so great. That deals with the first part. As I alluded to, though, that's sort of the easy part. So let's try to deal with the more difficult piece now. Now, in this part, I want to show that a of y is integrable. Okay, but what's a good way to show that this is a function of one variable, right? A of y. I want to show it's integrable. A good way to do that would be to show that this function a of y is continuous. Okay. Now, unfortunately, a of y is not like the restriction of some higher dimension. Like we can't just quickly apply some theorem here. So in order to do this, for the second part, we're actually going to look at like a of y minus a of y1 for some fixed point y1. Okay, so for this part, let y and y1 be in CD. And to help you out, I'm sort of thinking of y1 as being some fixed point. Y at some point I'm going to let vary, but they're always going to be in the interval CD. Okay. So let y and y1 be in CD. All right, if I just write down what is a of y minus a of y1. Okay. Well, by definition, that's okay, a of y is right here. A of y1 would be just plug y1 in there. But if I write down both those integrals, I can combine them. So I get that this is integral a to b of f of xy minus f of x y1 dx. All right. Now, sorry. Now I'm going to just slap absolute values on both sides of this. Okay. And now I can actually move the absolute values inside this integral, but remember when I move absolute values inside an integral, it potentially makes it larger. So this becomes the integral from a to b of the absolute value of f of xy minus f of x y1 dx. All right. Now, eventually what I want to do, I want to show that a of y is continuous. So eventually what I want to do is I want to say as y goes to y1, a of y has to go to a of y1, right? That's continuity. So I would like to be able eventually to express sort of what's going on here in terms of y and y1. Right now I have them trapped in sort of this function, this sort of function notation, and it's not easy to use the continuity of f quite at this point. Okay, so what I'm going to do is I'm going to just continue asking this question of sort of how badly behaved could this be? Well, one way to estimate an integral is to say, well, the worst this integral could be is you take the biggest value of this times b minus a, right? So certainly this integral is less than or equal to b minus a times whatever the largest value this integrand takes on over the interval AB. So this is, say, the maximum of f of xy minus f of x y1 for all x in AB. Well, note f of xy is a continuous function. So f of x when y is fixed is continuous, and f of x y1 is continuous when y1 is fixed. So these are both continuous functions. Difference of continuous functions is continuous. Absolute value is a continuous function, and the composition of so this whole thing here is a continuous function on the closed interval AB. It actually, by the extreme value theorem, must achieve its maximum and minimum values. I don't care about minimum, though. It achieves its maximum value. So I can actually say that this is equal to b minus a times, I can just use the absolute values here, times the absolute value of f of x1 y minus f of x1, y1 for some x1 in the interval AB. I don't know. In fact, there's not a unique one necessarily, right? It could achieve its maximum value at multiple places, but there's some value where it does. Okay. All right. Why does this help me? So then what happens? What happens as y goes to y1? So as y goes to y1, what's going to happen here? Well, as y goes to y1, remember, f is continuous. So as y goes to y1, f of x1y is going to go to f of x1y1, which means this term is going to go to 0. Well, if this term goes to 0 and this is less than or equal to that, but it's also, right, it's the absolute value of something, so it's greater than or equal to 0. So as y goes to y1, this difference goes to 0, which means this difference also goes to 0. And so a of y goes to a of y1. So what have I shown? I've shown that as y goes to y1, a of y goes to a of y1. So a is continuous. And therefore integrable. All right, this marker's that out on me a little bit. Integrable on CD, which is exactly what I wanted to show. Okay. And so that concludes the proof of this case. Now, if you wanted to prove the other case, prove that it's equal to the double integral of f is equal to the integral from a to b of the integral from c to d of f of xy dy dx, then you would basically do all this stuff, but you just switch around the y's and the x's in all the proofs. It's in spirit exactly the same proof, just with some slightly different bookkeeping to take care of. Okay, so that concludes the proof of this main theorem that continuous functions are integrable and that their integrals can always be calculated using iterated integration. All right, so that's all well and good. The continuous functions, they're sort of a nicely behaved class of functions in general. So, it's always nice if you can prove, if you're trying to prove that some condition holds and you're not sure, like starting with continuous functions and seeing if they satisfy, it's always sort of a good idea if you don't have any better intuition for where to start. They're nice, but maybe not too nice, right? They're not so nice as to be differentiable, let's say. So maybe you start trying to prove things are true for continuous functions. If you can't seem to do it, then you might take on a little more niceness. Maybe you try to prove it for differentiable functions or something like that. But it's nice to have a theorem that says if a function is continuous, then it's integrable. And as we mentioned in the previous video, this now makes like all of what you really do in Calc 3, like you can just think of double integrals as iterated integrals. Now, when you're teaching a Calc 3 course, I like to take a little time to try and tease out the distinction that the double integral is not an iterated integral. An iterated integral is a tool for calculating double integrals under certain conditions. But practically speaking, it's very difficult because 99.9% of the examples you're going to do in that course, you're going to calculate the double integral as an iterated integral. So it's a distinction that's hard to make, but for students who go on to do higher level mathematics, I think it's a good thing to at least start introducing them to. Okay. Now, the last thing I want to mention, if you think back to, say, 5610, right, we saw there that you can still integrate functions that are discontinuous, right? And so in particular, right, we prove something like, if a function has a finite number of points of discontinuity, then f is still Riemann integrable, right? So that seems, like sort of a reasonable theorem. Well, that's a theorem we know, but we might wonder sort of how does this translate for functions from, say, R2 into R? Now, you start to think about, okay, if I take a continuous function in R2, okay, right, so this looks like some surface. And I'm well aware that I always draw the same surface. I've probably mentioned it 100 times in this video or in these videos by now. Okay, so here's a nice continuous function. It's certainly integrable over any rectangle Q I might draw down here. Okay, so here's Q. It's certainly integrable over this rectangle Q. And so you might wonder, what if I came here and I just grabbed a point here, pulled it off, sort of popped it out, and just moved it up, right? My function now is still defined on Q. It's still bounded on Q. All I've done is take this continuous function and sort of pop out, and now I've got one point where my function is discontinuous. Like, I wonder if that will affect the integral. And if you think about it for a little while, you'll probably pretty quickly decide, oh, that's probably okay, right? What I could do is I could choose some partition of Q so that wherever this point of discontinuity is, if I come down here to where, I'll just sort of trap that point in its own little subrectangle of the partition. And then what I can do is I can make the partition, I can choose my partition such that this rectangle is really, really tiny. It's contributing very little to an upper or lower sort of sum. And so this really won't be a problem. Okay. And that intuition is exactly right. It's exactly the intuition that works for a one-dimensional case. It's exactly the intuition that works here. Right. And then you could ask yourself, well, okay, well, what if I go and I pull out, 2 or 3, 4 more points, right? Maybe I move this one down and I take this one and I move this one, I pull this one out and move it up, right? But you can again imagine, okay, I've just introduced a couple more points of discontinuity, and I could do the same thing. I'll just make sure, right? And as long as there's sort of finitely many of these, this argument will sort of work. And so that's fine, but you might wonder if you could do better than this, right? So for example, what if now instead of taking these finite numbers of points, what if I came up here and took some continuous curve on the surface? Okay. And I took that curve and ripped it out of the surface, right? Maybe I just relocated it up, right? Or did whatever, right? I could do, but what if I just sort of broke my surface right there and then relocated those points? Okay. Well, now my set of discontinuities in the plane, right now, it's no longer a finite set of points because in fact, I have like a continuum of points of discontinuity, right? So in fact, I have like uncountably infinitely many points of discontinuity. But somehow, like relative to the total area in Q, that's not a lot, right? I mean, it's a lot, but it's not a lot sort of as a percentage, which again, we can't quantify that in any meaningful way at this time. But somehow as a percent, it's not a lot of the rectangle, right? It's still a small fraction of the rectangle. So the question becomes, can we do something here even if we have, say, more than a finite number of points of discontinuity? And the answer is yes, but we need to be a little careful to define sort of what it means to have sort of not too many points of discontinuity. Okay. Now, I should also mention this theorem about a finite number of points, you can actually still integrate things that have more than a finite number of points of discontinuity. In fact, this definition I'm going to show you, you could use to work for other things as well. But let's take a look. So what we're going to do is we're going to define, so take A to be some bounded subset of the plane. Okay. In this case, we're thinking about like the rectangle. Okay, or sorry, we're thinking about a subset of a rectangle, really, right? Because we're integrating over a rectangle, but some subset of R2. A set A is said to have content 0 if, for every epsilon greater than 0, there is a finite set of rectangles whose union contains A, and the sum of whose areas does not exceed epsilon. Okay, so if we think about this definition, really what this is doing is generalizing this notion that we talked about. So if here's a rectangle Q. If I have a finite number of points, right? Let's say I have 4 points. Then I can always trap these points inside a set of rectangles whose union contains all of these points. So like imagine I take each of these, I just take some small rectangles here, and I can take them to be small enough so that, say, each of these has area epsilon over 4 for any epsilon you give me. And so maybe this is like A1, A2, A3, and A4. So the union of the AIs contains the set A. The set A is just the blue set, okay, the set of points. And the area of the union of the AIs, well, that area, these are disjoint, so it'll actually be equal to, but in general, even if these overlapped, it'll be less than or equal to the sum of the areas of each AI, right? Which in this case is just epsilon, okay? So we already, for finite numbers of points, this will certainly work, but you start to wonder, okay, what if I have other sets of, what if I have like some curve, right? If I just start with like a line segment. So what if my set of discontinuities just looked like this line segment? Well, I can cover this with a rectangle. Okay. Like let's say this is distance, let's say this is going from C to D. Okay. So I can cover this with a rectangle whose width is epsilon over D minus C, so that now the area of this is exactly epsilon. Okay, for any epsilon you give me, right, this is how I'll choose the width of my rectangle, and this rectangle will cover that entire set of discontinuities. What about other types of curves? Well, once we start talking about other types of curves, we have to probably add some additional restrictions onto the curve because we need to make sure that we can still cover these by some finite number of rectangles whose area doesn't exceed epsilon. But this general idea is that it's not about the sort of cardinality of the set of discontinuities, right? It's not about exactly how many they are. It's about how much area they take up, right? That's what this content zero is essentially saying, that there are some sets that really, you can always encapsulate them, you can sort of surround them by arbitrarily small rectangles. And so then when you go to actually like integrate, you can isolate those points out of really mattering. Okay. So the theorem that you end up getting is the following. Let F be defined and bounded on a rectangle Q if the set of discontinuities of F in Q is a set of content zero, then F is integrable. Okay. Now notice we don't get the iterated integration piece because now all of a sudden some of these A of Y things may not be continuous, they may not exist, they may not be integrable, but we do at least get that F is integrable. Okay. Now, as we sort of think about, how this works, the proof in spirit is very similar to the proof. You're mostly dealing with the fact that for most of the points in the set, this is continuous. So most of the proof goes the same as before. To just give you sort of a quick idea of how the proof works, the first step in the proof is essentially that you want to sort of isolate away the discontinuities from the other points in Q. Okay, so the first step is you essentially create a partition P such that the rectangles containing points of discontinuity have total area less than delta. Okay, so the idea is you make this delta and you go, okay, well I can, since my set of discontinuities has since my points of discontinuity have content zero, then cover them up with a bunch of rectangles whose total area is as small as I want, say less than delta. And so just build your partition so that those rectangles that contain the points of discontinuity have this. So this is really just using the content zero sort of piece. Now, you're going to define your step functions in a similar way. So we're going to define step functions s and t with s less than or equal to f less than or equal to t on Q in a similar way that we did before. So, except on the rectangles that contain points of discontinuity, or the subrectangles of the partition, where you'll set S to just be a minus M and T of X to be capital M, where M is just some bound on the absolute value of your function. Basically, just create these things so that they make sure your inequality here is satisfied. And on all these rectangles, the actual area of the rectangles is small, so it's not even going to matter what the values are here, as long as they're finite. Okay. The third step then is from all this, you then need to do that same sort of estimation from before. Okay. But now you have to take care to deal with subrectangles which contain points of discontinuity and ones that don't. And so what you can show is that this ends up being less than or equal to epsilon plus 2 capital M delta. Okay. So again, you do the same thing before. You choose the partition both so that this is true, and on the other rectangles, you want your maxes and mins to be within epsilon over b minus a times d minus c of each other. So working on those rectangles gives you this. Working on the rectangles that contain points of discontinuity gives you this. Okay, so you have to sort of establish that. And then finally, this has to hold. I can do this for every delta. So this holds for every delta greater than 0, which implies that this holds when delta goes to 0. But now this is exactly what we showed before, and this implies that the upper integral of f is equal to the lower integral of f, and hence this function is integrable. Okay. So, well, I haven't sort of worked out all the proofs in full detail, all of this proof in full detail. Hopefully this gives you some idea of how you might modify the proof. If you'd like to look at a full sort of more detailed version of the proof, page 365 in Apostle, that's chapter 11, section 11, does cover this proof, and we'll work out some more of those details for you. Again, what I really wanted you to see is that it is sufficient for a function to be continuous to prove integrability, but it's not necessary. We can still have integrability of discontinuous functions. The key here is that the set of discontinuities must somehow be relatively small, and small in the sense of area almost more than anything, in order to still have integrability. Now, we will actually, this notion of what it means for a set to be small is actually something we will continue throughout the semester, and will really be the focus once we get to measure theory of a lot of our study. So we'll be looking at this more in depth later on, but it's this will be the last foray for a little bit into that. So in the next video, what we want to do is we want to finally move past integrating on rectangular regions to more general regions. And we'll actually see that by defining the integral over a more generic bounded region in a particular way, we can actually make a lot of use of many of the theorems that we've already proven. So we'll begin that in the next video.